Welcome to Brain Vision.
In this problem on the topic of magnetic forces and the magnetic field, we are told that an electromagnetic rail gun consists of a conducting bar with a mass m and a length l. This conducting bar lies on horizontal rails and that is connected to a voltage source. Now, this voltage source maintains a constant current in the rails and the bar, and a constant uniform magnetic field fills the region between the rails. We want to find the magnitude and the direction of the net force on the conducting bar, as well as the distance the bar must move to attain a speed v, and then use this equation to find the distance that the bar must travel along the rails if it is to reach the escape speed for the Earth. So we are going to use the equation F is equal to ILB sine phi, where F is the force that will be exerted on the bar, I is the current on the rails, and B is the magnetic field. The acceleration of the payload, or the bar in this case, A, is equal to F over m by Newton's second law. Now, for part A, we know that phi is equal to 90 degrees, the angle between the magnetic field and the magnetic force. So this implies that the force acting on the bar is equal to ILB. And this force is to the right. So this will impart the maximum force onto the bar, allowing it to obtain a maximum final velocity. So now we know the magnitude and direction of the magnetic force that will act between the rails. Now for part B, we want to find the distance that the bar will have to travel to attain a speed v. So we can use the kinematical equation Vx squared is equal to the initial velocity v naught x squared plus 2 times the acceleration ax times the distance x minus x naught. But we know the initial velocity is 0 since the payload starts from rest, and the distance x minus x naught is simply d. So we can simply say that the final speed squared, v squared, is equal to 2ad. And if we rearrange this equation, we find that the distance that the bar needs to travel to attain a speed v is v squared over 2a. But remember, a we said was F over m by Newton's second law. So this is v squared times m over 2ILB. So now we have an expression for the distance d that is required for the payload to reach a speed v. And now we'll use this equation in part C to calculate the distance that the payload needs to travel in order to reach the escape velocity for the Earth and hence be able to leave the Earth's orbit. So d using this equation is v squared. The escape speed is 1.12 times 10 to the 4 meters per second, and that's squared, times the payload's mass of 25 kg divided by 2 times the current on the rails, which is 2000 amps, times 0.5 meters times the magnetic field strength. It's capital B, so the magnetic field strength we are told is 0.8 teslas. So with the given values, we get that the distance that the payload will need to travel in order to reach escape velocity is 1.96 times 10 to the 6 meters, which is 1,960 kilometers. So we can see that for the given values, this is inefficient.